Picture a detector scanning one image and evaluating tens of thousands of candidate boxes. Almost all of them are empty background, and only a tiny handful actually contain an object. That extreme imbalance quietly wrecked fast, one-stage detectors for years, holding them well behind their slower, more accurate rivals. Then a paper from Lin and colleagues, the RetinaNet paper in 2017, fixed the whole thing with one elegant tweak to the loss function itself. No new architecture, no complicated sampling scheme, just a smarter way of counting the error. It's called focal loss, and here's exactly how it works and why it mattered so much. To feel the problem, put the old loss and the new one side by side, because the difference is everything. The usual choice is cross-entropy loss, and it treats every example the same. That sounds fair, but remember the detector sees tens of thousands of easy background patches per image. Each patch contributes only a small loss, yet summed together they utterly dominate the gradient. The signal from the few real objects gets drowned out, so the model barely learns anything useful at all. Focal loss changes the emphasis entirely. It deliberately downweights the easy, well-classified examples and keeps the hard ones at full strength. Once the model is already confident and correct about a background patch, that patch essentially stops shouting for attention. Training then naturally concentrates on the difficult examples, the actual objects, and the confusing cases the model still gets wrong, which is exactly where the useful learning lies. Now let's walk through the actual mechanism, because it's simpler than it sounds. First, you compute the standard classification loss, the same cross-entropy you'd normally use. Nothing exotic here yet. This is just the ordinary measure of how wrong the prediction is for each candidate location. Then you check how confidently correct the model already is on each example. If it predicts the right class with high probability, that example is easy and not worth much attention. If it's uncertain or flat out wrong, that example is hard and genuinely informative, and it's the kind of case we want the model to obsess over. Next comes the key move. You scale down the loss on the easy, well-classified ones. A modulating factor, 1 minus the predicted probability raised to a power gamma, shrinks their contribution toward almost nothing, while barely touching the hard examples. And the result is that the hard examples now dominate the gradient. Without any complicated sampling tricks or hand-tuned heuristics, training automatically focuses where it matters, which is precisely why one-stage detectors finally caught up in accuracy. Now that we've seen the mechanism, 3 ideas capture why focal loss matters. First, the loss downweights easy, well-classified examples. That's the entire trick. By quieting the flood of trivial background patches, it stops the model from wasting all its effort on cases it already handles perfectly, and instead spends that capacity where the real learning is. Second, a single tunable knob called gamma controls the focus. Crank gamma up and easy examples get suppressed more and more aggressively. Set it to 0 and focal loss simply collapses back into ordinary cross-entropy. A value of 2 is the common default, giving a nice balance between calming the easy cases and preserving the hard ones. Third, it lets one-stage detectors handle extreme imbalance. That was the whole payoff. RetinaNet used focal loss to match the accuracy of slower two-stage models while staying fast, and the idea has since spread far beyond detection, showing up anywhere the classes are severely lopsided. Alright, let's lock in the essentials worth remembering. Focal loss solved the extreme class imbalance in dense, one-stage object detection, where easy background swamps the rare real objects. It adds a modulating factor to cross-entropy that downweights confident, well-classified examples so the hard ones keep their full weight. A tunable gamma controls how aggressively easy cases are suppressed, with a value of 2 being the usual choice from the RetinaNet paper. That single tweak let fast detectors finally match slower two-stage accuracy. If ideas like this click for you, You'll find plenty more computer vision concepts explained plainly at standarity.com.